So first of all, let's learn how to make this Pareto standardized chart. We'll make a simplified version for that. And to do that, let's use our example from this pilot plant investigation. You remember we created an Excel file with dataset with 16 rows and so on. So let's load this data first. So let me load the library, read Excel, and then load this data. Pilot plant, okay. So you can see 16 observations with 6 runs. Remember, we also have the randomized order of runs there, the replicates index, and also the factors and the y values, right? And then since I'm going to use ANOVA to make my Pareto chart, I need to convert all these values to factors, right? So I need to take temperature, convert it to a factor, column concentration, convert it to a factor, and also do the same for the catalyst. Well, first of all, I will convert it to data frame, because you remember that read Excel by default, it returns a table. There is nothing wrong with tables. It's a nice format, but I would like to use a simpler data frame format. Then I will use loop to make this conversion. So I say for example, F, meaning factor in, then I will use names. Let me just open this one to see the names. So it's temperature, concentration. I can also use indices, but with names I think it's a little bit more safe, so I will not make a mistake with the wrong index of my column. Then I simply say D, column F. You can use this double squared brackets to define the column. And then it's S factor, D, double squared brackets F. So let me see if it works. I will just click source, and then you can see all 3 now are factors. Okay. Now the next point is that I create a new model, AOV, and then I say I will make a full model, for example, Y, and then I say it's a temperature times concentration and times catalyst, then data equal to D, right? So that's it. And now the idea is that let me use this M object. You remember, let me show you summary M. Let me use M object to actually make a Pareto chart. Well, remember how we discussed it. That first of all, these F values, it's already squared standardized effects, right? So we need to find a way to get these F values and then take a square root. Okay, so that will be the first thing. And then you know that we have, like in this case, we have 7 effects, and then we have residuals, so we have 8 rows in total. We need only these 7 values because we don't have any F value for the residuals, of course. Okay. So first of all, how to get all these values? In fact, when you run summary, it returns you the result as a list. So if I save it somewhere, for example, to R, object R, you can see that object R is a list. By default, it has list of 1. It means it's just one model or one class. So you can see that the first element of this list, and inside you have all this information: degrees of freedom, sum of squared values, mean squares, F values, P values. All this information is there, right? So you see that it's like a nested list. So it's the first element. All these are first element of this list. So if I say take the first element of list R, you can see this is exactly the table that we have. And then, for example, if I want to get F values from this table, I can just simply take like this, and then you can see these are the elements of this table, then F value, and these are the F values. This is exactly what I want. And then you can see this is the last element, which is residuals, right? So let me get F values. So I say F vals is this one, right? Now, you remember that I first of all need to get rid of this one. But what I'm going to do, I will compute the number of values here. I will say length F vals. Then I simply say effects, standardized effects. It's a square root of F vals, but not all of them. Everything without N. So N, it's the last element. It's the length of this vector. It will be last element, right? So let me check it. So let me run it again. And then let me show what is inside. You can see this is 16.3, 3.5, exactly the numbers that we have seen before. But you can see that these are unnamed values, right? So we would like to have names. And luckily we have names here, right? So these are row names of this table. So what I can do, I can say names of standardized effects. take them from no row names of this R element list, right? However, you remember that we have more rows than effects. So we don't need the last one, so I will say we don't need the last one, right? So if I show you the standardized effect now, you can see now they are named. Yeah? What is next? Next, I will sort them. So standardized effects is sort standardized effects. And then I simply make a bar plot. Bar plot, standardized effects, like this. Okay. I think I forgot to run this one. Yeah, now it's sorted. Well, first of all, let's keep horizontal orientation of the bar plot. In this case, I add a parameter horis equal to true. Here we go. Very close to what we have, what we had before, right? And then what else? You can see that I don't have all the names correctly here. Why? Because of two things. Let me show you what I have as names. You can see names it has also a lot of spaces inside, right? So these spaces actually disturb all this information that we see here. Luckily, I know how to get rid of the spaces. I can use a function gsub, which can find any symbol in your string and replace it. So I say find a space and replace it with nothing in the row names. Yeah. So it will get rid of all spaces. Now you can see it's a little bit better. But you don't see all of them because you know that some of these values are pretty long. So you can see that, for example, again, if I show you the names, standard errors, you can see, for example, this is really, really long value, right? And this is why we don't see it here all correctly. How we can solve this problem? First of all, let's turn off the y-axis. So we don't have the y-axis at all, okay? So you can see that now we don't have any y-axis. And then let's make it manual. So we say axis, side number 2. So it's first side, it's x-axis, second side, it's y-axis. And then at which positions? So I need to know the positions of all these bars. Luckily, the bar plot actually returns me these positions as an output. So if I run it and then if I show you the numbers, these are positions of these bars. So I can say that just add equal to and then these p positions. But I don't want to show these numbers as positions. I want to show the names, right? So I say labels equal to and then the names of standard effects, right? So you can see now I added the names manually. You can ask, but nothing changed, right? So we still have this problem with names. Yes, but now we can add additional argument here. It's called las, and las allows me to rotate these labels, tick labels. Now if I run these two lines, you can see they are rotated now, and now you can see all of them. You cannot see all of them because we still have issue, and I see actually two issues. First of all, they are not sorted correctly. So let me run everything from the scratch. So they are sorted correctly. Now they are sorted correctly. Temperature has the biggest effect, but we also have another issue. We don't have enough place, enough space here for fitting all the values, right? This also can be tackled, and this is the idea. Look, any plot has margins. Margins, it's like an extra space that you have on left, on actually bottom, left, top, and right of the plot. And usually margin is defined in lines. It's a number of lines. For example, you can use here for labels, for X ticks, and so on and so forth. And by default, you have 4 lines here, 5 lines here, 2 lines here, and 2 lines here. Okay. You can get the current default values for margin if you use function par, which we used before to change any parameters of the plots, right? And then specify the name of the parameter. Then you can see it's 5422. Actually, the default values is 5.1, 4.1, 2.1, 2.1. I changed these values, default values, some time before. Okay, but these are the default values. Now what I can do, I can change this. First of all, I will save the default values so I can reset them. And then I can change them before I make the plot. And what I need to do, I need to change only the margin for the margin number 2, right? So this is the left margin. So we'll say margin equal to, I keep 5, and then instead of 4, I will write 10, and then 2. So I change only the left margin. Now, like you can see that I have enough space for all the labels, okay? And then, for example, if you, instead of real names, you can use, for example, the letters, Latin letters, then you don't need that many space that you can actually change margin and make it a little bit smaller. But it's important that we get back to the original margin after we made this plot. So other plots, the plots that you are going to make later, will have the default margins like this, okay? And then probably we need to add a box like this. Let me just do it again. This is better. So I think that we done almost everything. There is only one thing that is missing. It's this critical level, right? So we need to compute critical level and show critical level, like, for example, as a vertical line. You remember, to compute critical level, we need to use F-distribution. And F-distribution requires 2 degrees of freedom. It's the degrees of freedom of your effects. Let me show you the effects, right? So it requires this number and this number. And here we make a simplification. We will assume that degrees of freedom for all factors are the same. So I will take this value, and then I will assume that all other effects have the same degrees of freedom, okay? So I will take the first value and the last value. So it will be degrees of freedom for systematic variation and degrees of freedom for the random variation, okay? So let me get it. So I will just use the same idea, R, first element, degrees of freedom, and then first value. And that, let me call it df1, and df2 will be the last value number n. Let's check that everything is correct. You can see degrees of freedom 1, and then the second degrees of freedom is 8. So now we can compute the critical f value. We say use a quantile function for f distribution for 0.95% confidence, and then degrees of freedom 1, degrees of freedom 2, okay? And that's the critical value, right? It's 5.317 and so on. But you remember, here we have t scores, not f scores, so we need a t critical value. And luckily we can get one, we can compute one if we just use the square root of the f critical value, right? So in this case, you can see that it's 2.31 if we round it to 2 decimals, exactly the same as I used in my videos, right? Now let's add it. Let's say the AB line, vertical line at this critical value position. Let me make it a dashed line, and let me make it red. So now we have also the critical value, and perhaps we can also add it as a text, right? So let's say text. I know that, for example, here we have, let me just use, I know, P1, for example. It's the first position of the first bar, this one, right? So I will show the critical value here. And then let's say the y coordinate will be the same as the critical value. And then what I want to show the critical value itself, but I want to round it to 3 decimals. And then finally I say position equal to 4. It means it will be shown on the right side of this line. And that's exactly, oops, what I did wrong. Let me see. P1 is 0.1. It's, I see. I need to switch this. This will be y, and this will be x. So this is y, okay. Because this is the y values, right, where we have the bars. So let me just run everything from the start again. And now you can see this is here. Let me also make it red. And that's it. Okay. So that's a nice function we made. Now let's make it a real function. So I will reduce the space a little bit. Let me just call it Pareto effect plot. Okay. And then it's a function. It has only one main argument. It's m. And then I will add a couple of extra arguments in a minute. So let's move everything inside this. And then what else I want? I want to add a couple of arguments for labels. So xlab will be standardized residual. And then, for example, main title will be Pareto chart for, not residual, of course, effect, right? Effect. Pareto chart for effects. Like this. And then I simply add this to my plotting function. Where is it? This is it. So xlab equal to xlab and main equal to main. So let's try again. Let's load it first. So now you can see it's loaded to our environment. And let's call it, let's say, Pareto effect plot M. And then let's, you can see already that now we have all the labels, but let me make it like a clear experiment. So I clear it and then run it, and then you see it works. Okay. And there is one thing. Let's first of all check that it also will work if you have, for example, non-full model. For example, only main effects. Okay, let's see if it works. It does. You can see it shows only main effects. Of course, in this case, this is not fully correct because now we have one of the important interactions in the residuals. But anyways, at least the plot works well, right? And the other thing, for example, imagine that we don't use all data. Let me get back to full model first. And let's say we don't use the full data, we use only first 8 rows of this data. If we use only 8 rows, only first 8 rows, then we don't have enough degrees of freedom for estimating noise. And if we, for example, if you look at the ANOVA model, you can see we don't have any residuals, right? So we don't have any residuals. But if you make a Pareto plot, it shows some strange things because what it does, it computes the F values, but of course we don't have any F values, so it will be just nothing. Let me show you. It's just it's the old ones. Let me just do it again. You can see it's just null, right? And then we try to take a square root of null, which makes no sense at all, and then we see this error that taking square root of non-numeric argument makes no sense. Okay, so let's make it nicer. Let's simply do the following. Let's check if n, for example, it's a number of values in F values, right? Smaller than 1, then we make a nice error message. So stop. And then, for example, the let's write just cannot compute standard error. Lack of degrees of freedom, for example. Oh, just standard. Let's just keep it like this. Okay. That's it. Let's try it. Let's reload the function first, and then let's run it. And then you can see this is the error message. Okay, that's actually it. Now let's move it to our cut and paste to our script, DOE tool script. Here we go. I paste it at the end, save it, and I think that's about it.